everyone, for today's lesson we are going to learn how to simplify numerical radical expressions, and we're also going to be able to add and subtract radical expressions. But before we get started with today's lesson, I would like you to please go ahead and practice evaluating expressions that have rational exponents. So I want you to take 81 and raise it to the 3/4 power, then 25, raise it to the -3/2 power. Then I want you to take the 4th root of 16 and then raise it to the 5th power. For each of these expressions, when you simplify them, I do not want you to use a calculator. I want you to try to simplify them without a calculator, because on this portion of the test, you will not be allowed to use a calculator. So I want to make sure that you're prepared for the test. When you have an answer, go ahead and restart the video and we will see how well you did. Alright, so when I'm looking at the number 81, I always think of either 9 squared or 3 to the 4th power. 3 to the 4th power was one of those numbers that I said we use often, and it's one of those expressions that I need you to know and memorize. So I'm going to work with that. 81 is really 3 to the 4th power. So I'm going to replace the number 81 with 3 to the 4th, and I'm going to raise it to the 3/4 power. What I'm now going to do is multiply the exponents. This is technically 4 times 3, which is 12, and 12 divided by 4 is 3. So this is equal to 3 to the 3rd power, and 3 to the 3rd power is 27. So our answer is 27. Next we have 25, and whenever I think of 25, I always think of the base of 5. This is 25 raised to a negative exponent. That does not mean our answer is negative. It means that we need to flip our base around. So this is going to be equivalent to 1 over 25 to the positive 3/2 power. I'm now going to replace the number 25 with 5 squared, and I'm going to take 5 squared and raise that to the 3/2 power. So I'm going to multiply straight across. 2 times 3 is 6, and 6 divided by 2 is 3. So this is 1 over 5 to the 3rd power, which is 1 over 125. And that is your answer. Next we have the 4th root of 16 to the 5th power. I think that it's helpful to rewrite these problems using bases and fraction exponents so that you can simplify it a little bit easier. But if you want to work with the roots, that's perfectly fine as well. So I'm going to take 16 and raise it to the 5/4 power, because 5 is my exponent and 4 is my root, and it always is exponent over root. Next, whenever I think of the number 16, I always think of the number 4. So I'm going to write 4 squared is being raised to the 5/4 power. 2 times 5 is 10, and 10 over 4, that's really equal to 5/2. So this is 4 to the 5/2 power. Unfortunately, I still have a fraction exponent, so that tells me I need to keep going. And whenever I think of the number 4, I always think of 2 squared. So I'm going to rewrite this as 2 squared raised to the 5/2 power. So 2 times 5 is 10. 10 divided by 2 is 5. So we end up with 2 to the 5th power as our answer, and 2 to the 5th power is 32. That's something that is going to occur a lot. 2 to the 5th power being 32, and the 5th root of 32 equaling 2. That's something that we use very often in this class. Hopefully for this warm-up you did pretty well, and simplifying these expressions are becoming easier for you. I recognize that it's a little weird, but hopefully it's becoming better. If you're struggling with it, please feel free to come and see me after school or email me any of your questions. So for today's lesson, our learning target is for you to be able to say, I can simplify numerical radical expressions. So that means that I'm going to give you square root, cube root, 4th root expressions with just numbers underneath. And I'm going to give you a couple properties that are properties that we've already used when it comes to square roots before, but we're just going to be applying it to other types of roots. And like I said, it's numerical radical expressions. So that means in this lesson, we're not going to be working with variables. We'll be working with variables in the next lesson. The next I can statement is I can add and subtract like numerical radical expressions. So we're going to be working with like numerical radical expressions. And I'll talk about what like means when we get there. So the first part is multiplying and dividing radicals. So what that means that we're going to be doing is whenever you see a product underneath a square root, a cube root, any root for that matter, you can separate it. Separate the multiplication by taking the root of the first term times the root of the second term. And likewise, if you end up with a product of a root times a root, you can put it under one root as a product. So you can go back and forth between this. So what I mean by that is this. Let's say that we were talking about the square root of 2 times 16. That's equivalent to the square root of 2 times the square root of 16. And then we can rewrite this as 4 times the square root of 2. On the other hand, let's say that we have the square root of, like the cube root of 4 times the cube root of 2. We can combine these roots together to make this the cube root of 4 times 2, which is equal to the cube root of 8, and we know the cube root of 8 is 2. So both ways, that's what this property is talking about. You can expand or separate your product, or you can bring it back together as one product under the root. It just depends on what is given to you, but that's what the product of properties of radicals represents. The quotient property says that if you have you're taking the same root of a numerator and denominator, you can take the root of the numerator and you can take the root of the denominator. And you can go backwards with it. So if your numerator and denominator are related to one another, it might be helpful to rewrite it as one fraction. So what else? I'll give you a quick example. So let's say that we're talking about taking the square root of 2 over 25. 2 and 25 have nothing in common with one another, so we can't simplify this fraction any further. So it's in our best interest to just take the square root of the numerator and divide it by the square root of the denominator for us to get our answer of the square root of 2 over 5. Or you might end up with a problem where you have, let's say we have the cube root of, let's say we were talking about the cube root of 75 divided by the cube root of 3. So then that would be equivalent because 75 and 3 are related to each other. 3 can go into 75 evenly. We would take the cube root of 75 over 3. And 75 divided by 3, that's equal to 25. So this is equivalent to the cube root of 25. And there's nothing further for us to simplify because 25 is not a perfect cube number. So that's what I mean by going back and forth. Now, as you guys can see here, we're working with roots that could potentially be in our denominator. So that might mean that we might have to rationalize the denominator. So that might be something that we have to do in these problems. So our goal is to make sure that we rewrite these expressions in simplest form. So what does simplest form look like? Well, it means that it's a radical with an index of n. So what that means is that if you're taking the nth root, the square root, cube root, fourth root, whatever it is, that means that there are no perfect nth root factors under the radicand. So the radicand, which is the stuff underneath the root, has no perfect nth root powers, and it has and any denominator has been rationalized. So whenever you rationalize the denominator, that means that you'll multiply the top and the bottom by what it needs to eliminate the radical. So here we go. Example number 1. We're just going to analyze all of these without a calculator. So the first thing that we have is the cube root of 125. Whenever I think of 125, I think of the number 5. So I'm going to rewrite this as the cube root of 5 cubed times. We have the number 8. The number 8 is the cube root of 8. Well, we know that 8 is 2 cubed. And the cube and the cube root will cancel out for both of those. So I'm left with 5 times 2, and that's equal to 10. Now, is that the only approach for this problem? No. If you saw right away that the cube root of 125 was 5, and the cube root of 8 was 2, and 5 times 2 is 10, that's beautiful. I am absolutely okay with you doing that as a way of showing work. That's not a problem. It just depends on what you see. So that was letter A. Letter B, we have the cube root of 96 over the cube root of 3. So we have a cube root over a cube root, so I would encourage you to ask yourself, can 3 go into 96? Well, it actually can. So I'm going to rewrite this as the cube root of 96 divided by 3, and I'm going to simplify this fraction. 96 divided by 3, that is 32. So this is the cube root of 32. Now, 32 has perfect cube factors in it. So you have to think and ask yourself, what perfect cube number is a factor of 32? And thinking of all my perfect cubes, I know that 8 is a perfect cube number, and it can go into 32 evenly. So I'm going to rewrite this as the cube root of 8 times 4. So what I did here is I thought about perfect cube numbers that can go into 32, and I know that 8 is a perfect cube number, so I rewrote this as 8 times 4. If you want, you can separate this by taking the cube root of 8 times the cube root of 4. And we know that the cube root of 8 is 2, so this is 2 times the cube root of 4. 4 is a perfect square number. It's not a perfect cube number, so that means that we would just leave it under the radical. If we were multiplying by another 2 underneath, or we had a multiple of 3, and with respect to our exponent, we could do something about it, but this is simply our answer, 2 times the cube root of 4. Looking at letter C, we have 245 divided by 5, and we're taking the square root of it. Fortunately, 5 can go into 245, and that is equal to 49. So I'm going to take the square root of 49, and that is equal to 7. Some of you might be asking to yourself, when do I use the plus or minus? And plus or minus is only used whenever we're solving equations. So we would not have a plus or minus if we're taking an even root unless we are solving an equation. And in this case, we are not. So now let's go ahead and look at letter D. For letter D, we have the cube root of 432. And 432 is not a number that we traditionally work with. So whenever you see numbers that you're not familiar with, what I would recommend is rewriting that number on the side. So I'm going to write 432. And I'm going to divide 432 by a prime number. The easiest prime number that I can tell will go into 432. And since 432 is even, the easiest prime number I'm going to work with is 2. And since we're taking a cube root, my goal is to identify a perfect cube number. Thinking about all the perfect cube numbers that we know of, from 1 to 10, and my goal is to try to find one of those. So 4 divided by 2 is 2, and 32 divided by 2 is 16, so this is 216. 216 is a perfect cube. This is equivalent to 6 cubed. 6 cubed is equal to 216. So that's awesome. I have identified a perfect cube number that can go into 432. So I'm going to rewrite this as the cube root of 2 times 216. And if you want, you can separate this into the cube root of 2 times the cube root of 216. And the cube root of 216, that's going to be 6. So this is 6 times the cube root of 2. And that is your answer. Let's go ahead and look at letter E. For letter E, we have the cube root of 104. Once again, 104 is not a number that we work with often. So what I would recommend that you do is on the side, break 104 down. Try to identify a perfect cube number, that is something that can go into 104. Well, I don't know 104 off the top of my head. I don't know a lot about it, but what I do know is that it's even. So what I'm going to do is I'm going to divide it by 2. 104 divided by 2, well, that's going to be 52. Well, 52 is not a perfect cube number, so I'm going to take that 52 and I'm going to break it down even further by dividing that by 2. Well, 52 divided by 2 is 26. So even that doesn't really help me because 26 is not a perfect cube number. But I do know that 26 is even. So I'm going to keep going. and divide it by 2 again. And I know that 26 divided by 2 is 13. Okay, so 13 is a prime number, and I can't even break it down anymore. But this is what I do have. I have 2 times 2 times 2 times 13 is equal to 104. That's one of the cool things about breaking down each of your factors, is that we're able to now have the cube root of 2 times 2 times 2 times 13. And since this is a cube root, we are looking for something to the third power. And technically, 2 times 2 times 2 is really 2 to the third power times 13. So we can split this apart into the cube root of 2 to the third power times the cube root of 13. The 3 and the cube root will cancel out, leaving us with 2 times the cube root of 13. And that is your answer. Some of you might be saying to yourself, is that the only approach? The answer is no. There's so many other approaches. Some of you might have been able to see right away that 8 is a factor of 104, but other people might not have seen that. So what I just showed you is a strategy. And anytime that you have a cube root, or whatever that root is, as soon as you have that number of factors inside, meaning that we're taking the cube root, and I had 3 2's and being multiplied by themselves, notice that there was 1 2 that came out of your answer. It's just a strategy and just an idea that could potentially help you. Let's go ahead and look at letter F. For letter F, 10 and 27 have nothing in common, but it might be helpful for us to break it down as far as we can. The number 10 doesn't have any perfect square numbers, so I'm just going to rewrite that as the square root of 10. But I do know that 27, well, I know that that's equivalent to 9 times 3. So I know that the square root of 9 is 3, so I have 10 divided by 3 square roots of 3. So I've simplified my denominator, but I have a root in my bottom, and we're not allowed to have roots in our bottom. So I'm going to multiply the top and the bottom by the square root of 3. And by doing that, I end up with the square root of 30 divided by 3 times the square root of 9. That's 3 times 3. And 3 times 3 is 9, and the square root of 9 is 3. So I have the square root of 30 over 3 times 3. And that is the square root of 30 over 9. Now, although 9 and 30 have a 3 in common, this 30 is under the root, so you cannot take anything out. 9 doesn't have a root around it, so you cannot simplify the square root of 30 and 9 any further. This is simply our answer. We have 2 more examples, and then we're finished with this first portion, and then we have a really quick example that's coming up next. So for letter G, we have the 4th root of 32 times the 4th root of 8. 32 is a perfect to the 5th power, 5th root, but other than that, it's not to the 4th power, it's not a perfect 4th root. And 8 is a perfect cube, but we want to take the 4th root of it. So what might be helpful is to simply multiply these 2 numbers together. So I'm going to multiply 32 times 8. And when I multiply 32 times 8, I end up getting the number 256. So 32 times 8 is 256. Now, I'm sure that not many of you guys know a lot about the number 256. So what I would do is I would take that number 256 and break it down until I find something that is to a perfect 4th power. Now, the only perfect 4th power that I know of is 2 to the 4th power, which is 16. That might be something for you to know and for you to memorize and study. 2 to the 4th power is 16. And if I can at least get down to a 16, or break it down so that I can find a group of 4 numbers that are the exact same, that might be a good thing. So I'm going to divide 256 by 2, and I end up getting 128. Well, 128 is not a perfect 4th power, or at least I don't know that it is. So I'm going to take 128 and divide it by 2, and I end up with 64. Well, 64, I know it's a perfect cube number and a perfect square number, but it's not necessarily a perfect number to the 4th power, so I'm going to keep breaking it down. 64 divided by 2 is 32, but 32 is a perfect 5th power, so that's really not going to help. So I'm going to take 32 and break it apart into, or divide it by 2 again, and I end up with 16. Awesome. So what that means is 2 times 2 times 2 times 2 times 16, which I just told you was a perfect fourth root. That means that I'm going to, I have everything that I need in order to break this down. So I'm going to rewrite this as 4 times the fourth root of 2 times itself 4 times 16. So what this is 2 to the fourth power, because it's 2 times itself 4 times, and then 16 is a perfect fourth power root. So I'm going to rewrite that as the fourth root of 2 to the fourth power times another 2 to the fourth power. The fourth root of 4, they cancel out, leaving us with 2, and then once again the 4 would cancel out with the other expression. So we have 2 times 2, which is 4. And that's our answer. And finally, we have the 3 times the cube root of 32 times negative 2 times the cube root of 4. So these parentheses are here to confuse you. We're not adding or subtracting anything. We're simply multiplying. So I'm going to multiply my outside numbers times my outside numbers, and my inside numbers times my inside numbers. So I end up with negative 6 times the cube root of 32 times 4. 32 times 4 is 128. Well, 128 is not a perfect cube number. 125 is, but 128 is not. So I'm going to take 128 and I'm going to try to break it down. So 128 divided by 2, that's 64. Well, 64 is a perfect cube number. We know that 64 is 4 cubed. So I can stop breaking it down right now because I just found myself a perfect cube factor. So I'm going to rewrite this as negative 6 times the cube root of 2 times 64. So I can break this apart into negative 6 times the cube root of 2 times the cube root of, I know that 64 is 4 cubed. The cube and the cube root eliminate, leaving us with negative 6 times 4 times the cube root of 2. Because all I did was I eliminated the cube and the cube root to leave me with the 4, so I'm just going to bring the 4 right next to the 6. And negative 6 times 4 is simply negative 24. So this is negative 24 times the cube root of 2. And that is your answer. All right, so now we're going to add and subtract like radicals. So what does it mean for 2 radicals to be considered alike? Well, like radicals means that everything is exactly the same. So like radicals is where they have the same index. That means that you're taking the same root. So you're going to have, like, both of them are going to have a cube root, or both are going to have a square root, or whatever the root is, that they're both going to be the same. Next, the radicand, or the stuff underneath, is exactly the same. So the same stuff underneath. So the same exact stuff under the root. Now, radicals can be added or subtracted if the index and the radicand are alike, if they are exactly the same. So let's go ahead and look at letter A. For letter A, we have 7 minus the cube root of 12 minus the cube root of 12. So whenever you're combining like terms, look at them as if they're variables. So if we were working with variables, this would be just like 7x minus x, and that would be equal to 6x. Well, the same thing goes here. We have 7 times the cube root of 12 minus 1 times the cube root of 12. So this is equal to 6 times the cube root of 12. 12 doesn't have any perfect cube factors in it, so this is simply our answer. There is nothing further for you to do. For letter B, unfortunately, we both have the same, or they both have the same index. We're taking the cube root, but underneath is not the same, so we need to adjust each of them. So what I would recommend that you do is simplify each expression individually. So looking at the number 81, I know that the number 81 is 9 squared. So I'm going to work with 9 squared, which I know also that 81 is also 3 to the 4th power. So maybe that might be the better approach. And it might even be helpful to rewrite this using fraction exponents. Just putting that out there and then going back to radicals. It's just an idea. Or I don't know. Here's just a few options. So I'm just going to write down a few things. I know that this is the cube root of 3 to the 4th power. So what that means is it's equal to the cube root of 3 times itself 4 times. Well, I'm looking for a group of 3 because this is a cube root, and I have a group of 3 3s. So this is really the cube root of 3 to the 3rd power times 3. So all I did here was I rewrote 81 as 3 to the 4th. I expanded it to show what 3 to the 4th really means. And then I was able to find a group of 3 3s. So this is 3 to the 3rd times an additional 3. The 3 and the cube root would eliminate for the first part, leaving us with 3 times the cube root of 3, because this 3 is left over. So 3 times the cube root of 3. I'm going to write minus going straight down, and now I'm going to work with the number 24. Well, 24, we want to try to figure out, are there any perfect cube numbers that can go into 24? And in this case, we know that 8, 3 times 8 is equal to 24, and 8 is a perfect cube number. So I'm going to rewrite this as the cube root of 3 times 8. I know that the cube root of 8 is 2, so this is minus 2 times the cube root of 3. So I'm going to rewrite this as 2 times the cube root of 3 until I finally reach where I was at before. So now look at where we're at. We have 3 times the cube root of 3 minus 2 times the cube root of 3. Both of these have the same root. They both have the same number under the root, and all we need to do is combine the numbers in front. 3 minus 2 is 1. Our answer is simply 1 cube root of 3. So what I did for this problem is I worked with each term individually, simplified it as far as it could go, and then I was able to identify the fact that they have the same root, and then I just added the numbers in front. And finally, for letter C, we have 2 to the 2/3 power and a 2 to the 2/3 power. Believe it or not, both of these are considered roots. This is like the cube root of 2 squared, and this is the cube root of 2 squared. So just like before, whenever you have two expressions with the same, that are like radicals, we would just simply add the numbers in front. So our answer is going to be 12 times 2 to the 2/3 power. There's nothing further for us to simplify, and if our problem starts off in fraction exponents, it'll end in fraction exponents. That is the end of this lesson. If you have any questions over anything, please feel free to email me. Otherwise, I hope you have a wonderful day.